It seems like science is increasingly being done with advanced detectors on enormous ground and space-based telescopes. One might wonder, is there anything left to learn from observations made with digital cameras mounted on approximately 10 cm telescopes? The answer is yes, plenty. Illustrating this point, a new study using such equipment recently reports on the structure and dynamics of the Sun's corona during 2 solar eclipses. Observations from small telescopes have provided this beautiful view of the solar corona during a solar eclipse in 2013. These data have helped researchers better understand what shapes the larger-scale structure in the corona. Alzat et al. 2017. A full view of the corona images taken during the solar eclipse in 2012. The central color composite of the eclipsed solar surface was captured by SDO. The white live view of the solar corona around it was taken by the authors, and the background, wide field black and white view is from LASCO. The white arrows mark the atypical structure. Alzat et al. 2017. The solar corona is the upper part of the Sun's atmosphere, extending millions of kilometers into space. This plasma is dynamic, with changing structures that arise in response to activity on the Sun's surface, such as enormous ejections of energy known as coronal mass ejections (CMEs). Studying the corona is therefore important for understanding what drives its structure and how energy is released from the Sun. Though there exist a number of space-based telescopes that observe the Sun's corona, they often have limited fields of view. The Solar Dynamics Observatory (AIA), for instance, has spectacular resolution but only images out of 13 of a solar radius above the Sun's limb. The space-based coronagraph LASCO-C2, on the other hand, provides a broad view of the outer regions of the corona, but it only images down to 2.2 solar radii above the Sun's limb. Piecing together observations from these telescopes therefore leaves a gap that prevents a full picture of the larger-scale corona and how it connects to activity of the solar surface. To provide this broad, continuous picture, a team of scientists used digital cameras mounted on approximately 10 cm telescopes to capture white light images from the solar surface out to several solar radii using a natural coronagraph solar eclipse. The team made 2 sets of observations, one during an eclipse in 2012 in Australia, and one during an eclipse in 2013 in Gabon, Africa. In a recent publication led by Natalia Alz at Honolulu Community College, the team now reports what they learned from these observations. Building atypical structures same as the previous figure, but for the eclipse in 2013. Alz et al. 2017, the author's image processing revealed 2 atypical, larger-scale structures with sharp edges, somewhat similar in appearance to what is seen near the boundaries of rapidly expanding polar coronal holes. But these structures, visible in the southeast quadrant of the images taken during both eclipses, were not located near the poles. By analyzing their images along with space-based images taken at the same time, Alzit and collaborators were able to determine that the shape the structures took was instead a direct consequence of a series of sudden brightenings due to low-level flaring events on the solar surface. These events were followed by small jets, and then very faint, puff-like CMEs that might otherwise have gone unnoticed. The fact that such innocuous transient events in the Sun's low atmosphere can be enough to influence the corona's larger-scale structure for timescales of 12 to 48 hours is a significant discovery. There are roughly 3 CMEs per day during solar maximum, suggesting that atypical structures like the ones discovered in these images are likely very common. These results therefore have a significant impact on our understanding of the solar corona, which goes to show that there's still a lot we can learn with small telescopes. Impact of the passage of a series of puff-like CMEs shown in the LASCO time sequence in the bottom panels on coronal structures. Alzat et al. 2017 citation Natalia Alzat et al. 2017 APJ 848-84, DOI 10.384715384357AA 8 Candelas 2 related journal articles Discovery of a new class of coronal structures in white light eclipse images DOI 10.10880004637X785114 Exploring the prominence corona connection and its expansion into the outer corona using total Solar eclipse observations DOI 10.10880046337X79321119 Identification of low coronal sources of stealth coronal mass ejections using new image processing techniques DOI 10.384715384357AA6 CAA Thermodynamics of the solar corona and evolution of the solar magnetic field as inferred from the total solar eclipse observations of 2010 July 11 DOI 10.10880046337X734212 erupting filaments with large enclosing flux tubes as sources of high-mass 3-part CMEs, and erupting filaments in the absence of enclosing flux tubes as sources of low-mass unstructured CMEs DOI 10.10880046337X813135 First detection of prominence material embedded within a 2 times 106 kcme front streaming away at 100 to 1,500 kilometers S-1 in the solar corona DOI 10.384720418213AA7460 This post originally appeared on AAS Nova, which features research highlights from the journals of the American Astronomical Society.